Welcome back. We will now go into the more technical talks in this workshop. The first one will be on atmospheric radar system and techniques by Dr. M. Durga Rao. Durga Rao has been associated with the National Atmospheric Research Laboratory in various activities, and we are fortunate that he was also a member of the technical committee of the DST SCRB National ST Radar facility, which has come up at University of Calcutta. There have been various occasions when we had to undergo extensive tests at Horinghatta as well as at the site of the manufacturer in Hyderabad. And Durga Rao's expertise and guidance has been a very strong factor in determining the present status of the system that we find, that tomorrow you will also witness during the hands-on training that we are planning at Horinghatta. So without much further ado, let me invite Dr. M. Durga Rao, National Atmospheric Research Laboratory, to deliver his lecture.
Thank you very much, sir, for your nice introduction. Actually, I am very happy to be part of Kolkata ST Radar team development, and we thought that I was thinking that my activity was completed because already it was commissioned. But in fact, with the inspiration of our director NARL, to see that how the not only development in this area, but all the students of this region, how to get the benefit by using the facilities of both NARL and Calcutta University ST Radar, which is one of the state-of-the-art development has been completed recently. So in that way, I am very happy to be again to come back to Kolkata. Okay. So actually, Director NARL has given an overview of all the instruments that are being used or developed at NARL. Out of that, he might have used so many keywords. Always used to say that high power radars and this radar is useful for studying the mesosphere or stratosphere or troposphere, or sometimes this will be used for some of the planetary missions. So a lot of keywords he used. And some scattering he has used, and the range, what is the resolution, those things, the temporal resolution, those things he has used it. So what exactly the meaning of that? So what exactly a radar, how it is useful for not only for studying your hard targets like your aeroplane or ship and those other things, other bodies, how this is useful to study the atmosphere also. That will be seeing his one, and how it is basically works, how a radar works, and how it is bringing the position of the target or the velocity of the target, or how it is useful for one atmosphere region to other atmosphere, how it is useful, that and all we'll see. So this is my topic, that is the MST, as already he told, this mesosphere, stratosphere and tropospheric radar, and I will be just touching upon what exactly there in the subsystems. So what are the building blocks like our brain and our eyes and other major subparts. So what exactly are there to contribute this total system to work like a radar, those things we'll see, and also what are the different techniques, how to work, whether I have to run or I have to jump or what I have to do to get different things. So those things I will touch upon in the techniques part. Okay, so first we'll start with the radar. So maybe to go with, to refresh your things, because I am seeing that some of the students are here and some faculty members are there from different communities. I'll just start from the basic of the radar. What exactly means by radar? So radar is nothing but a RA, it is nothing but radio wave, that is detection and ranging. So basically a radio wave is nothing but a RF wave that you are aware with high frequency radio wave that is transmitted in the atmosphere or in the space, so that it will detect some of the targets in the atmosphere, and the reflected back signals, once it goes back to the radar system, it will find out some characteristics of this target it will provide. Maybe how much far from this radar it may be giving, or how much velocity or how much speed it is coming up or it's coming away from us, those information will be going. Okay, so this is basically the radar. And what exactly there in the radar? this is a fundamental block diagram, like without this a system cannot work. So basically consists of a transmitter system which will be generating the RF wave, whatever the radio frequency signal that is generated by this radar, the transmitter, and to radiate into the atmosphere certainly we should have antennas. So that is an antenna, and once the signal is coming back, so you can see here when you are transmitting it is a high power, it's a large signal with a peak very high amplitudes, and when it comes back with the scattering that we'll see, it's very very weak signal it is there, that's why traditionally it is shown small signal here, amplitude, and once it is received here, it has to be certainly received by an receiver system, like in the analog domain it has to receive, and then it has to be translated into the digital domain for the signal processing or data processing applications. And in between these two, we have a duplexer. It's like a via media, like a transmit receive switch. So basically, if you are based on the mode of operations, we will be having bistatic radars or monostatic radars. Usually all our ST radars are monostatic radars, that means it is having the same antenna will be used for transmission as well as reception. So that's why we are using, since the antenna is common, we are using the duplexer to provide the facility between transmit time, it will be giving the path to the antenna, and the receive time, it will be giving the path to the receiver. So this TR switch translates between transmit and receive. Okay, this is the bistatic, means sometimes what happens, separate antennas will be there for transmission as well as separate antenna system will be there for reception. So based on the application that we'll be having, so that we'll see. And here also we have pulsed radars and Doppler radars. Two types of radars are there, and what exactly is that we'll see in the next slide. So what exactly a pulsed radar means? Just my application is very simple, that I don't know what is the distance at which the far away wall is there or some object is there. So what I will do, simply I will, if I am a radar system, if I am transmitting, I will just send a transmit pulse from here, from my thing. So, and once it goes there, and once it hits any target, and once it comes back, I will just measure the delay between these two, and based on the delay, I can get back the range. So maybe some 15 meters away from me, the wall is there, or some AC is there, or object is there. Like that, some distant target I can get by using this simple pulse radar technique. So how I will be getting the target range? The same, that time t equal to that onward path when the transmitter is sending the signal to the target, and when it comes back from the target, the total time traveled is t. So the target range will be given by r equal to c into t by 2, because it is traveling both onward path and receive path also. So it will be simply ct by 2 I can get back, and where c is the velocity of the EM wave, it is equal to 3 in 10 power 8 meter per second. And sir, some question may be there. Sir, if I am using this one, how far I can go? When I am sending the signal, how far it may go? So based on your because they say the pulses, radar pulses are not only single pulses, so several pulses have been, it will be transmitted. In the first slide when Dr. Patra has shown by Woodman, some 316 pulses he has used for integrating the signal. So like that, based on the application, some number of pulses will be sent based on the target characteristic. Maybe ionosphere means less number of pulses, or if it is coherent high, we can send more number of pulses. So based on that, let us say the pulse between first pulse to second pulse, the time is called as interpulse period, IPP. Based on this IPP, the maximum unambiguous range, that means if I am sending one pulse without any ambiguity, I can, within the total range, I can find out total number of targets, what is the, whatever echoes are there, I can, without any ambiguity. That means whether that person one is sending or some other echo pulse is sending, that one, without any ambiguity, I can get back by using this R equal to, unambiguous is equal to C into IPP by 2. So only one thing is here is, in the pulsar radar, I am saying always that how much distance I am getting the echo, but I don't know whether it is moving with 1 meter per second or 2 meter per second or 10 meter per second, that I don't know. Whether it's reaching near to me or is going away from me, I don't know. So Doppler, I am not sensing about anything about the Doppler. So here only timing only I knows. So to get the Doppler information, there is other technique like Doppler radar. They are also called as continuous wave radars. That means there will be two antennas. From one antenna, continuously it will be transmitting, and there will be another antenna. After hitting the target, it will be receiving the signal. So the Doppler information, it is transmitting, and there will be other antenna to continuously will be receiving. So I can get back the, I will be measuring the phase of the signal, the received pulse whatever is coming. So A cos omega t, once it comes back, when sending that cos omega t signal, the phase information based on the path length, the 2r, so that one from that phase I can get back d phi by dt. If I am doing, I will be getting the Doppler frequency I will get. From there I can get the Doppler velocity by using fd into lambda by 2, where lambda is the operational radar wavelength. So here one thing is that I can get back the Doppler information also. That means velocity of the target I can find out. Previous technique I can find out the range. So if I combine both the techniques, that position also I will be knowing and the velocity also, Doppler information also I will be getting. So these two will be just integrated and will be like the radar is called as coherent pulse Doppler radar. So pulse Doppler radar, it gives both range information as well as your velocity information. So that's why all our ST radars are, whatever MS radars, they are coherent pulse Doppler radars. And here previously we have seen it's a discrete target, that may be one target in the atmosphere I will be sensing and I will be getting the information from that. But an atmosphere is not like that. It is a continuous layers of information is there. So when such a continuous information is there, how to get back that range information, how will I will be getting? That information is shown here, that is called as range gating of the radar. So here I will be sending a small pulse, that is transmit pulse. When this goes into the atmosphere, the range after after t equal to, after the pulse width, this tau is the pulse width and this delta is the TR switch delay time to switch between transmit and receive. Then I can get the samples in the receive period. These dots are the receive period, that is time series points. So what I can get from the first range, I can get one pulse to the radar, that is equal to R equal to from the pulse resolution of R equal to CT by 2 from that region, this delta. So CT by 2, that is pulse volume, I can get back first sample in the time series point. Similarly, from the next R equal to C into 2T, next transmit pulse, I will get back one more information like that. At each pulse resolution, that is range resolution of CT by 2, I will get back 1111 time series point I can get, and in that way total up to the total interpulse period I can get back the all the information in the pulse, in the atmosphere radars. So in the discrete radars, like if a discrete target is there, only one time or one target is there, means I can get back. But here continuous information also, by using the range gating, we can get back the signals like this. Okay. So after seeing this, now we have seen that two types of radars are there. One is for hard targets, other for soft targets. Now all the atmosphere is only, we are talking about only soft targets. So what are the targets of this atmosphere radar? In the morning session, sir has told that the atmosphere, like we have troposphere, stratosphere, over that mesosphere and ionosphere above that. So what happens in how this atmosphere will get back me signal? I don't have anything, target is not there to me. I am not having a person which is flying over that, so that I can point to that and I can get back. So here thing is, when the atmosphere, and yesterday night I think you have some humidity was here is more, and we have rain. So humidity is one of the point here, and we have the partial pressure changes are there, and temperature changes are there, and also we have temperature changes. So in the atmosphere, right from Gadanki, if you see, that is from Tirupati to this location, if you see, as sir told, 5 ST radars are kept at different locations. Each location having, in the troposphere, different atmospheres. Similarly, when you are going in the atmosphere, every region has different atmosphere changes are there. When you go from surface of the earth to the troposphere, almost like tropopause for our tropical altitude, it's 16 to 18 kilometers. So there will be a decrease in the temperature, almost like 4.5 degrees per Kelvin per kilometer will be there. After that, again it will be increasing in the stratosphere, almost like 20 kilometers to 50 kilometers. So it is a stratosphere region. After that, it is a mesosphere. So there is a temperature changes are there, and also apart from these temperature changes, there are humidity changes are there. That is, pressure changes are there, and once you go to the ionosphere, there are neutral atmosphere is not there. There are free ions. So in the atmosphere, we have different changes are there. So all this turbulence, all these changes contributes to the turbulence or the refractive index fluctuations it will be causing. So that is the target of our radar. So basically, the refractive index perturbations or changes in the refractive index, they are the targets for our radar. That's why since they are soft, we are calling it a soft target, or it is called a soft target radar. If you are going for a like a aeroplane or any other satellite or any other meteorite, they will be the hard targets for our radar. So from now onwards, we'll be calling these radars are clear air radars or soft target radars. Okay, so how to characterize this one? The refractive index changes, these all weather changes of temperature, pressure and those things will be causing the refractive index changes. That is shown in this equation. Basically in the stratosphere region, it is dominated by pressure and temperature. In the tropospheric region, it is a partial pressure and temperature changes. When you go to the ionosphere, it is mostly dominated by the free ions. So all these terms in each region, they will be dominating. It is in the stratosphere, troposphere and ionosphere. So the atmosphere refractivity is given like n minus 1 in 10 power 6. That is nothing but it is mostly in the neutral atmosphere is dominated by first two terms. So when you are neglecting the ionosphere part. Okay, so this is the target of our radar. Since once a target is there, when I am sending the atmosphere, electromagnetic wave, what happens to the wave? When I am talking to you, my wave is coming to you, reaching to you, it is going to the walls, some reflections are happening, or some absorbers if they might have kept, it is getting absorbed and it is dying down. But similarly, when I am sending an electromagnetic wave in the atmosphere, what happens to that? Certainly, it has to be scattered. What is meant by scattering? Just think that after this workshop or after what will happen, everybody will be just scattered from this room. You may be going to your home, you may be going to some other Kolkata University or some other classes, or some people may be staying here. You just simply will be scattering from here. That means in your all the directions you will be going away from here. Similarly, when the electromagnetic wave is propagating to the atmosphere, it is having different scattering mechanism will be there. The wave will be basically scattered. And some of the waves, whatever is sensitive to us, whatever is coming back to us, very few things will be there. That one very less amount of energy, that whatever is coming back to the radar, that is only useful to study for our applications. That's why these radars will be so powerful. We will be transmitting very large peak powers and your return signals will be very, very, very weak. So what are the different types of mechanisms, the scatterings we are having? We have Bragg scattering, Fresnel scattering, Fresnel reflections are there, especially for clear air radars. And once you go for the higher frequencies, the Rayleigh scattering dominates there. So that we'll see how the scattering mechanism works. Especially at UHF radar, UHF frequencies, that is VHF frequency and UHF, mostly it's lower part of the UHF. That is what is VHF frequency? 30 MHz to 300 MHz. That area, this Bragg scattering mostly predominates. What is Bragg scattering? You can see from here, this is a radar and it is transmitting one signal in the atmosphere. It is simply scatters. That means the wave is just scattered into the different directions and some part of the energy is reflected here coming in this area also. When you see the refractive index changes when you plot with respect to the range, let us say from here to here, if you are having a range in the vertical axis and refractive index changes on the x-axis if you plot, it is some fluctuations are there. If you apply Fourier of that, we can see that when the refractive index, the irregularity size when it's equal to lambda by 2 from here to here, it is periodic. That means the change from here to here again is periodic. That means something is happening there. So when the irregularity size is when lambda by 2, there is a periodic nature. What exactly it does here? You can see here, when the electromagnetic wave signal is transmitted here, corresponding to lambda by 2, what is the path length that will be going from for a lambda by 2? 2 pi by lambda into lambda by 2. So 2 pi is nothing, 360 degrees, and lambda by 2, 2 pi by lambda into lambda by 2. So lambda get cancels, 2 pi into lambda by 2 is nothing but 180 degrees, that is pi. So when you go from here to here, there will be a phase shift of 180 degrees contributed by this wave in the forward direction. Let us say the wave is coming back from here. Again in the received direction, again at 180 degrees, phase shift will be created, and when you compare here, both the phases are equal. That means whatever exactly the phase I am sending to the that layer, when it comes back from the irregularity size of lambda by 2, again I maintain the same phase. So that is useful for me for radar processing. So this type of scattering mechanism is called as Bragg scattering, or also it's called as back scattering, that is coming back to me. So this is one of the scattering technique. And what are the other scattering techniques that we have? When you go for higher frequency radars, especially more than L band, S band, those things. So there what happens, let us think that this is the irregularity is having, the target is having size of r, and the circumference is 2 pi r. So when you compare the lambda, that is the radar wavelength, lambda, when you are comparing with the circumference of that target, that is size of the target, if your wavelength is more than your circumference, then Rayleigh scattering will be predominant. And the other way, if your radar wavelength is exactly equal to your circumference of that one, then there will be resonance regions will be there, then my scattering will be taken into the picture. And suppose if your frequency is very higher and your lambda is very small and your target size is somewhat higher, then it is called as geometric scattering, or you are entering into the optical region. To better understand these things, you can see here, this is the curve that is showing the different parts of the resonance, especially in the Rayleigh region, when the lambda is better, bigger than your circumference, and when it is both are same, it is a resonance period, it will start here in this region, and when lambda is much smaller than your circumference, it goes to the optical region. To better understand in your physical dimensions, this plot you can see, let us say we have 300 megahertz radar, which is for around 1 meter. For this size, you have here having a raindrops, which is a very less than a centimeter. It will be because the wavelength is better, more than this your size of the particles. Mostly the Rayleigh region, it will be falling in the Rayleigh scattering region. Suppose the same raindrop, when you are going for 30 gigahertz or maybe more than 10 gigahertz radar type of thing, the same raindrop will be giving my scattering when compared to the Rayleigh scattering at the lower frequencies. So what you have to understand is, similarly, if you think the birds which is having few centimeters, even at 3 gigahertz like S-band radars or C-band radars itself, mostly the type of scattering comes from these birds, and those things will be my scattering rather than the Rayleigh scattering at those frequencies. So there is a dependency of the type of the frequency based on your target requirements. So based on that, this different type of scattering mechanisms will be used, especially for our ST radar or our MS radar, where it operates at 50 megahertz. Most likely the Bragg scattering will be predominant, because mostly that lambda by 2 irregularity size, scale size is around 3 meter size that we are having, that we are concentrating on that. And till now we have seen that there is a radar and different types of scattering mechanisms are there. So now for Calcutta University type of thing, I want to design a radar for understanding or for studying your mesosphere, stratosphere and your ionosphere and those type of things. So what I have to do? What are the different considerations I have to design a radar? So that is basically told here. First is the operating frequency is very much important. So for MSc region I want to study VHF. I told VHF is the most better thing. So that's why around 50 megahertz, 53 megahertz radar you have selected, and this is the type of the waveform and bandwidth depends on the type of the radar. So what type of waveform I have to send, whether in the pulse, what type of pulse I have to send, how much length I have to send, how much time I have to send, what is the interpulse period I have to make it, those and all, and how much bandwidth of the radar system I should use, that also one of the important point. And also the power. Just now we have seen that these are Bragg scattering or your back scattering is happening. So the signals are not all the signals are coming back to our radar. Very weak, very less part of the signals only coming back to my radar. So the transmit power should be very high to get back that much of weak signals to the radar. So that also plays an important role while designing your radar and your antenna aperture. Just like that one antenna if I am keeping, whether how much power I can radiate into the atmosphere, that I don't know, because it will be the gain of the single antenna will be very less. So how much area I have to use, whether previously in the last talk we have seen that GCOMARC or somewhere almost like 300 meter by 300 meter type of that much big area it was used. And our MS radar, if you see in the coming slides, we will be getting 130 meter by 130 meter type of array size we have used. So why that much of array size is required? How it will increase the gain, that and all, how we will decide that how much aperture is required, that also we have to consider while designing the radar. And also when it comes to the receiver time, your signal is very weak and almost is buried under noise. So how much time I have to integrate so that the receiver power will be just above the noise, so that at least detectability level I will be bringing, and then I will be giving to the digital resource system for signal processing. So the noise floor I have to make it very minimum to have the better detectability. That I have to design as per the requirements. And also if I am where I have to keep my transmitters. If I am keeping my transmitters inside and the antennas are outside, there will be system losses will be there and sensitivity will be somewhat lesser. So there should be appropriate place where I have to minimize the system losses and I have to keep my instrumentation even though they are high power. So those are all conditions we have to while designing a radar. Now by keeping all these factors in mind, there is for designing a radar based on your type of scattering, this radar equation has been by using this radar equation we can design your radar. Basically this is the PS is the received signal power, that is characterized by PT is the transmit peak power, GT is antenna gain, transmit antenna gain, GR is the receive antenna gain, but most likely for monostatic radar both GT and GR are both are same, so we can call as G square. And in the sigma is the radar cross section. That means what is my target, how much I am sensible for the this radar, that is detected by this radar, that is by this radar cross section. And in the range, it is inversely proportional to the fourth power of the range. It is for any hard target, this radar equation holds good, but this is the factor, that sigma is the factor where by using the different type of radars with different type of scatterings, the sigma will be changing. Then according to that your radar parameters will be changing. So here we consider the case of our VHF radar, ST radar. Since it is not a hard target, it is not having it is having volumetric targets based on if I am sending a pulse width of tau, the range of it's a pulse volume of CT by 2. From that CT by 2 I will be getting total echoes. From that one the sigma is given as the pulse volume into eta. That eta is called as the radar reflectivity. Based on the type of scattering for the eta will be changing. Here we are having Bragg scattering, for that eta is 0.38 into Cn square into lambda to the power of -1/3. And these are all the other CT by 2 and pi theta square, that is E plane beam width and H plane beam width, those factors we have to consider here. And by using all these things we will be having the received power calculations we will be having. Okay. So here when you are having not only having transmit power, the receiver also should have minimum noise figure. For that one the atmosphere noise is given as, receiver noise is given as KTB, where K is the Boltzmann constant, TS is the system noise temperature, and B is the bandwidth. How much matched filter bandwidth I should use it, so that atmosphere losses other atmosphere noises I can remove, and I can improve sensitivity. That factors I have to consider here, so that I will be having reasonable signal to noise ratio when you are dividing this PS by PN. And here most important thing is, whatever the peak power into the aperture comes from antenna gain, 4 pi AE by lambda square, that is nothing but a gain. So by these two, product of these two, peak power and the antenna aperture is known as the figure of merit of any radar. If my figure of merit of my radar is high, I can detect very sensitive echoes also, even very weak signals I can get. And also I can classify based on the power aperture product only, it is called as MSC radar or ST radar or tropospheric radar or other boundary layer radar. So that one we will be seeing in the next slide. So as I told, this is a PA that determines your total classification. For a boundary layer boundary layer radar like a LOPI, which works in 1 L band region, if you have a power aperture product of close to 10 square, that is 100 watt meter square if you are having also, we can go from 100 meters to 4 kilometers of height coverage, we can have it. And if you want to go for only tropospheric region, even 10 cube, that is 1000 watt meter square if you use, that will be sufficient, so that the low power system can go up to close to 10 kilometers we can go. And if you want to go for almost like up to 20 kilometers you want to go, minimum power aperture product is required is 10 power 8 or better. So especially these ST radars, especially in the VHF region, either 50 MHz, close to 50 MHz or 200 MHz, these systems will be designed. And if you want to go for mesospheric and those echoes also, which are very sensitive and weak, so those information also if you want to get it, you certainly should go more than 10 power 8 power aperture product. So based on this the classification of radars will be coming. So if you have the radar equation, and if you properly design your transmitted power, your aperture and your beam width, how much is required and those things, then we can design a radar as per this, and we can further classify these radar systems in which class they will be going. Okay, so now we will see that I know that radar equation. I have designed my system, and I know that this is a MS radar type of system. What exactly there in the system? So what is transmitter? I know about transmitter. I should have more peak power and the antenna array. I should have more aperture size I should have, and more antenna gain I should have, and the receiver system also should be very sensitive to detect the VKKs also. Then how to realize these type of things? I know only on paper I have designed everything. Whether on paper when you design, whether the system will be realized? Certainly not. So when you are realizing, what are the important things that are required, that we will be seeing from now. So this is advanced image radar. Actually this is when NMR was there, this MS radar which was built in 1993, which was having semi-active phased array configuration. That is, we are having triode tube type of transmitters we are having. Each triode tube with a maximum peak power of 120 kilowatt used to be there, and one transmitter used to have like some 32 antennas that used to be powered. But what happened in the due course, maintenance of that radar became very tough, and triode tube and those became obsolete, and then we entered in the new era of electronics. Like solid state devices have come, and it is giving better performance when compared to your solid state, your triode tubes. But the only thing is large powers realization is little bit tougher. So for that, what it is done, the new active array technology has been implemented, and here the active array means each antenna is have its own TR module. That means each antenna has its own phase shifter will be there, and its power amplifier will be there, so that each antenna is independent. Like everybody, we are having our own mobile, we can communicate to each other at different places, rather than your land phone in a house where all of your family members you are using the same land phone. So now it's almost like a mobile phone, like each antenna is having its own capability to radiate and receive. So what is the advantage of this type of state-of-the-art technologies? It has modularity. That means I can use a part of the system or full system, or if in future if I want to augment also, I can augment as per the requirement. So that is the modularity that brings for this modularity, and multi-receiver capability. If I am having multiple receivers, what is the advantage that we will be seeing in the future slides? Imaging we can do, interferometry applications we can do, that is possible with this system, and also improved sensitivity. Since the TR modules are kept right in the near to the antenna field, so when the system losses are minimized, so my noise figure in the receive path noise figure will be reduced, and indirectly it will be improving the sensitivity, and also when you are transmitting here, then there won't be any loss, and total peak power I can radiate from the antenna system. And also one of the most important factor is the 360 degrees beam agility. That means anywhere in the azimuthal plane I can steer the beam by using this active phased array technology. That we'll see how we'll be getting the electronic beam steering in the next slides. And what are the different systems, important systems that are there in this one? Here we have seen the antenna array and the TR modules, that is transmit receive modules. There will be transmitter and receiver, and there is an exciter. It is the exciter where exactly if I want to transmit a 53 mega signal, so that signal is usually generated at the exciter path. It is having a high stable OCXO, Owen controlled crystal oscillator is having, with respect to 10 MHz OCXO, the 53 MHz signal or any other signal for the radar, maybe 200 MHz if any radar is there, the 200 MHz signal it will be generating, or if it is 53 MHz signal, 53 MHz low power signal will be generated by using the exciter. Once this exciter is generating low power signal, I am having various TR module, large number of TR modules, this has to be distributed to them in equal amplitude and equal phase by using this RF distribution systems, and the path losses, whatever the distribution when I am doing, I will be, because if I am, let us say if I am having a big cake, I want to, maybe some 100 people are there. So how much amount of cake I should have to equally to give at least 10 grams or 20 grams of the cake piece to equal to all of you. If I am bringing maybe half kg of cake, is it sufficient to you? It's not sufficient. So maybe certainly I should go maybe a 10 kg cake or something. So then only I can give maybe 100 grams or 10 grams for each of you. Similarly, when you are distributing the signal power into the large number of TR modules, there will be conversion loss. That loss has to be compensated by using the boosting amplifier. There is a class A type of power amplifier is there here, so that it will be boosting the water conversions losses in this master distribution control unit, and further it will be distributed using other networks. So in that way, the generated signal at 53 MHz low power signal is distributed to TR module at low power, and then the required peak power is generated using the field located TR modules, and then through the antenna array they will be radiated into the atmosphere. So once in the atmosphere, a scattering, maybe it is a Bragg scattering or maybe Fresnel reflection or Fresnel scattering, whatever it happens, the reflected back signals will be coming first to the antenna array, and through the antenna there is a low noise amplifier in the TR module that will be amplifying the very low weak signal first at this place, and then similarly, like we are having here 1024 TR modules, 1024 numbers of signals are combined here into a one type of thing, and then finally is given to the analog receiver. So your matched filtering and removing the noise from the other frequencies will be done here, and required amplification will be done in the analog receiver, and then finally is given to the digital receiver, where till now it is in the RF domain you are having the signals, then it is converted into the digital domain, and further it is given to the computer for processing. So this is happened at digital receiver system. So analog to digital conversion will be happening, and other signal processing steps are implemented here, and finally is given to the signal processing PC, data processing PC. There will be doing various type of signal data processing steps. And to control all these people, like your teacher, you are controlling your in the classroom, maybe one fellow is sleeping, one fellow may be chit-chatting, those type of things, no? Like a moderator, there is a moderator for this, for radar also, that is called as radar controller. It is called as brain of the radar system. This is controlling all the subsystems. So if we are having 1000 numbers of TR modules, we are having different subsystems, because all are to be synchronized to a particular command that is done by the radar control system. And also various experimental parameters, maybe I want to operate in the lower atmosphere or maybe in the ionosphere, those sheet parameters also will be configured in the radar controller. And this is where you will be seeing like a different subsystems. The RF subsystems all are enclosed in these two racks, like the exciter, RF distribution system, your analog amplifiers and digital receivers are equipped here, and they are the control distribution networks are kept in other racks, and this is the antenna array. So in that way the signal once is generated here through this distribution network goes to the antenna array through the TR modules. So these are the basic specifications. The radar which is having at NARL works at VHF frequency, that is 53 MHz. Since we are having 1024 antennas each and 1024 TR modules, here each TR module gives 1 kilowatt of peak power. So 1024 numbers will give more than 1 megawatt, 10 power 6 watts of power it will be generating, and the antenna array size is 130 meter by 130 meters. It's almost more than a football ground. So with that large power aperture, almost our power aperture product is more than 10 power 10, 1.73 10 power 10. And in the previous classification we have seen that if you are if you want to classify into ST radar, minimum 10 power 8 should be there, power aperture product, and our power aperture is almost close to 10 power 10. And these are the various parameters, and wherever the subsystem they are coming, that I will explain you there. Okay, and we'll just go into the different subsystems of the radar. First one is, most important one is antenna. Without that, I cannot communicate to any other person. So you have your mobile, in your mobiles also lot of antennas are there. You have different type of patch antennas, so are different shapes they will be making based on your type of communication. So here for our radars also, based on the frequency of applications, there will be various types of antennas are there. Suppose if you might have seen that for your weather radars type of thing, there will be a dish antenna. Or in your ATM centers, on the top of that ATM centers you will be having for satellite communication, they will be having small dish antennas. So there are some type of antennas for one type of frequency application, and especially for our VHF or HF radar application, Yagi antenna is the better one. It is having a folded dipole antenna it is also called as. It basically uses dipole, and with other elements it is called as Yagi. It has one director which is above the folded dipole, and one reflector just below this folded dipole to concentrate to send the energy towards the folded dipole. And if you are going for high frequencies like more than L band, you will be having different patch antenna systems. So that will be using, or especially if you are going for X band or those things, for a larger phased array systems, you will be mostly using this patch antenna systems. So here this is E-plane beam width, usually it will be around 70-75 degrees will be there in the E-plane beam width, and H-plane beam width will be around close to 120 degrees. That means it's having wide beam, that's what I want to say here. And this is the reflection coefficient once you are measuring in the field, it looks like this, and this is centered at 53 megahertz, which 10 dB beam width more than 4 megahertz. And here surprisingly we have two antennas here, you can see. Actually here one antenna is shown. Here we are having two antennas and for the same boom for east-west polarization, north-south polarizations. For previous radar configuration like semi-active phase radar, for initial MS radar, there is two antennas were used. One polarization switch was there, which is switching between east-west polarization, north-south polarization. But since we are having now active phase radar systems where you are having each antenna has its own TR module, you certainly doesn't require two antennas, even one antenna is sufficient. That's why in Kolkata University here you can see only one antenna is there. Tomorrow if you are coming there also you can see only one polarization is sufficient, that is kept in north-south polarization. So this is regarding the antenna system. And now we have to see that one interesting question previously we asked. In the morning also sir was telling like 300 meter by 300 meter antenna aperture used. Some places 130 meter by 130 meter aperture is used. Why that much of large number of antennas are required to use? I can keep one antenna and one TR model, I can just send it. So why we are keeping this many numbers? The interesting thing is, as in the previous slide we have seen that one antenna gives almost a beam width of 70 degrees minimum. And in H-plane if you are going 120 degrees. So it is having wide beam width. So but if I want to communicate to the large, far away distances, your energy should be concentrated. Like a pencil B type of beam is only required to get back. The power spectral density will be higher if you are having narrow spectral width. So best example is you take a small torchlight and you use a laser, which is more powerful. Laser is certainly powerful. It is having more energy in the very sharp pencil beam. But if you are torchlight, what will happen? It will just go for some distance and after that it will just scatter. It will not go for long. The same thing is in the aperture, when you want to go certainly almost up to 100 kilometers, or certainly you have seen that even moon also sometimes. So that much of long distances we want to go, you should have larger apertures so that your beam will be becoming narrow. That we'll see how it will form, until the power spectral density when the echoes are coming up, that will be more. And what happens when you are using large aperture, so many number of antennas when you are using, how to control them? Even in a class, if nowadays more than 30 number of people, it is very difficult to control them. Each person is different. One fellow may be using his mobile, one fellow may be using maybe writing something. So when this many antennas are there, and each fellow is individual, my pattern is different, that fellow's pattern is different. How to get the uniform narrow pencil beam? How to control them? How to use them? So we have some 5 controls are there. How to use in a large systems. One is the geometrical configuration of the antenna. Whether I am keeping them in a rectangular shape, the aperture wise, this room is kept in a different way, like some curved nature that your seats are kept, right? So instead of that, maybe some benches will be there. If I am organizing them in a rectangular fashion I can use, or a square fashion I can use, or I can use them in a circular phase. So that one also matters for the antenna when you are radiating, when you are generating radiation pattern, that is important. And also the spacing between the elements. Like you people, when you are coming closer to you, you can chit chat much better way. One fellow can interfere to other person, correct? But if I am keeping you, when your exams time, what happens, whether they will sit you like this, you will certainly not sit in this with that much close spacing, because you will interference will be more. So the spacing between antennas also here as a major thing is there, so that the importance of this spacing will come in next slides. So at that time I will show you. The spacing also matters very much here for the beam scanning as well as reducing the mitigating the mutual coupling, and also the excitation amplitudes of individual elements. Each and every antenna is important, and each antenna amplitude, whether I have to feed them equally, or for one person I will give more food and other fellow I will be giving less food. So that also matters, that we will be seeing in the coming slides. And also the relative pattern. One fellow is having 70 degrees beam width pattern, other fellow is having maybe 30 degrees pattern, like different antennas if I am using, it will be certainly different. But here in our case we are using all are similar antennas, so this will not be coming in the problem, and other things we have to control for the phased array when you are using. This is what I was showing. So we can keep them in a square grid. It is a square grid, and the lattice between that, it is between the structures, the pattern is called as lattice, and overall shape is called as the grid. So here it is, our antenna is a square grid with square lattice, and we have 30 MHz radar that is called as Giri radar, that is kept in a rectangular grid is there with rectangular lattice. So here it's like the spacing in the north-south direction is different, the spacing in the east-west direction is different. And here when it comes to Kolkata University radar, this is a circular grid with triangular lattice. So the advantage of this one is, when you go with these two type of radar, configurations, you will be certainly, when you are increasing the number of antennas, your overall antenna gain will be increasing. But only thing is, the side lobe level will be with uniform linear distribution, it will be 13.3 dB. That means from the major lobe to the first side lobe, the difference is only 13.3 dB. And if you are going for the circular grid, it will be around 18.69. So more than the side lobe level, which is actually side lobes are not required lobes. That's why it should be minimized as much as possible. So this type of configuration is much better when compared to this type of configurations. And I was telling, the interelement spacing is so important. So how much wide I have to keep them, whether I have to bring them close or I have to tell them to go away from that. So this is, you can see here, let us say if I am keeping, this is a square grid, it's, if I am using, that is let us say east-west direction also I am having 0.7 lambda, and north-south direction also I am having 0.7 lambda spacing I am having. With this type of spacing, when you are going for a beam steering, when you are doing, that means when you are tilting the beam electronically, that we will see again next in the coming slide. When you are steering the beam, how much maximum I can steer the beam, that is decided by this physical spacing of the antenna. By using this formula, d by lambda equal to sin theta. So the theta is the how much tilt I have to give from the vertical direction. That depends upon this interelement spacing d. If close spacing is there, I can go for more scanning angle. But only problem is, when I am bringing closer and closer and closer, what will happen? The mutual coupling start predominant. Like you people will be chit-chatting when you are coming closer and closer, closer. They also will interfere with one fellow to other fellow and have it will affect further on the transmit system or receive system. So when we have to decide how much angle, maximum angle for my scientific applications I have to go, and then I will be designing this radar with this type of spacing. But if what happens with the same type of square grid, instead of using this, if I am going for a triangular lattice, this is called as triangular lattice, what will happen? The distance between this in the east-west direction, if you see, east-west direction it is 0.7 lambda, and between this element and that element also side is 0.7. But only thing is, because of your equilateral triangle property, your height will be root 3 by 2d. So what will happen, even if I am using 0.7 lambda, the effective spacing will be 0.6 lambda. So with this, I can go in a much better way scanning in the north-south direction. I can go 41.8 degrees, I can go rather than 25.3 degrees scan angle. This is the advantage of using a triangular lattice when compared to a square lattice. This is the advantage that why we are gone for this type of lattice in Kolkata University radar. And maybe some more question may come. Sir, you are telling that maximum scan angle, it is limited. I don't mind, just I will go with 0.7 lambda, but I will steer my beam to 50 degrees. What will happen? So the answer is here. So if I am using for a particular, this is a particular case for Giri radar, we have used 0.56 lambda spacing. So up to 52 degrees, this is the main beam, I have steered my beam electronically. I kept here like this. But surprisingly, I want to give, I will adjust the phase in such a that I will go whatever it may be. So what happened, when you go away almost like more than 52 degrees phasing if you are giving, there is one more fellow has come into the picture. So this fellow is unwanted fellow, this is a grating lobe. This unimaginary, previously this fellow was here, it is in the imaginary plane, but it came into the reality. Now what will happen, whether I am using this beam or this beam, I was not knowing. The echo comes maybe coming from this direction or this direction, or whether I am transmitting my beam this direction, I don't know. So the grating lobe certainly affects the measurements. So the spacing of the antenna is so important, so that your beam steering is limited by that one. So that is where we have to design our radar by using different type of configurations. And also, in order to keep the lobes, side lobes to much lower, we have different antenna thinning techniques. That is also one of the things is antenna tapering technique, so that the major lobe And this, if you are not using any tapering for a uniform linear distribution for square grid or other configuration, usually 13.3 dB down will be there. But the same thing, if I want to bring it down, there are techniques. We are using maybe Taylor technique or Kaiser or Hanning, Chebyshev. That means amplitudes. I will not feed them in equal amplitudes. I will be feeding them in a different pattern so that I can bring down the side lobe levels to the required levels. So that's where we can play, even though one configuration when you are using, in order to bring down, we can configure by using this type of techniques. But only problem is, when you are using this type of techniques, your beam width will be little bit broader and your efficiency also will come down. If you are not using any taper, totally 100% will be illuminated, but when you are going for tailoring, you are applying, you are not using full peak power. So the efficiency of the peak power will be coming down almost like 64% when you are using for a Taylor and for a 24 dB, 20 dB down if you want to bring down the antennas, that means first side lobe level. Okay, so 10 minutes. Yeah, so now we'll see different phase array systems that we have used it, and mechanical systems we will be using. In the morning also it is told that there will be mechanical steering will be there, that we have servo systems in the azimuthal plane and elevation plane, so that we can steer the antenna for weather radar applications. Usually this type of or any scanning radar they will be using this one for tracking radars type of thing. But our radar antenna itself is not in a single antenna. We are having very large number of antennas. How to steer them, it is not possible. So we are using the concept of electronic beam steering, so that the antennas are not physically steering, they are just stationary. By adjusting the phases between the antenna systems, we can steer electronically rather than steering them physically. That we'll see how we'll be doing. You can see this uniform linear array with a spacing of d. If you are seeing a far away object, up to here the phase front will be more or less same, but this is the additional space, that is d sin theta, when you are tilting the beam to the theta from vertical direction. If you are tilting this one, there will be d sin theta path has to be extra, the first antenna has to travel when compared to the signal receiving the second antenna. Similarly, first antenna second antenna has to travel d sin theta higher phase, it has to travel, path length is to travel when compared to third antenna. So this is where if you want to tilt the antenna, this will be the extra paths have to be has to be traveled by these signals to the individual antennas. If you use this type of concept, the d sin theta extra I have to use between first antenna to second antenna to third antenna. So that is d sin theta extra element is called a progressive phase shift. So if I am properly using d sin theta, d sin theta, d sin theta, d sin theta, if I am progressively controlling between the antennas, I can tilt the antennas in a particular direction for a uniform linear array. For planar arrays, that is having antennas in x-axis and y-axis also, if I am having, if I want to position my beam in some theta direction and phi direction, so use this formula, that is 2 pi by lambda into d sin theta in x-axis sin theta cos phi and 2 pi by lambda into dy sin theta sin phi. If I know my theta and phi and I know the geometry of the array, by using this formula I can get back the progressive phase shift. If I am giving progressive phase shift to the individual TR modules, the advantage you can see here. If I am not using progressive phase shift here, between the antennas, and simply each antenna is radiating, as such individually you are radiating on your own, and you are coherently you are not forming any beam here. It is your beam is just like it is going in a particular direction, a beam is not formed. But if you are using this progressive phase shift and you are controlling this phase shifters of the TR module in a proper way, because of the constructive interference, the beam is formed in a particular direction, in the theta phi direction, and other directions there will be some side lobes, but in your required direction you will be forming the beam. This concept is called as electronic beam steering. So if I want to have a particular direction, theta phi direction, if I want to fire the beam, just use this formula and progressive phase shift to calculate. According to the geometry, you feed them to through the radar controller, and your beam will be positioned in the direction. If I want to change my direction, again based on theta phi, again calculate and feed to the TR modules. This is called as electronic beam steering. And once I am knowing the electronic beam steering, and also I should know whether I am properly feeding my progressive phase shift correct or not. That also we can simulate using this softwares, and we can check whether my beam is properly forming or not. Radiation pattern I can check. This is one example I am seeing for a grid radar I am showing here. Here I want to, we have calibrated the radar, and progressive phase shift has been calculated and kept to the the required phases have been given here, and you can see the beam is forming towards north 14 degrees direction. For ionospheric radar from Gadanke location, we should have a north 14 degrees direction so that your beam is perpendicular to the magnetic flux lines, and you will be getting back the echoes strongly from that direction. So in that way, the progress phase shifts you can calculate, and you can feed to the simulation softwares, and you can cross check also. So this is where I want to show this one. And the second important thing is, I was telling there is an exciter system which is generating the your low power RF signals. The pulsed RF signals will be looking like this, and once based on your pulse width, that is tau, your range will be decided by this one. And if I am using 8 microseconds signal here, the width is, if it is 8 microseconds, I will be getting the echoes from the pulse volume of 1.2 kilometers. But for a lower atmosphere applications, if I want to study the atmosphere maybe with 150 meters or 37.5 meter more resolution, then I will be going for the coding techniques. Here complementary code will be used. So complementary codes, I think you can see here, there are certain codes are there, like ED, E2, there are some binary codes are there. That one, when you are using with your signal like a BPSK modulation, when you do, this type of signals will be generated. This in turn, these signals will be transmitted and get back the echoes for improving the range resolution. The advantage here is the pulse width we are not changing. So total pulse width may be from here also 8 microseconds, here also 8 microseconds, but by using the code, the effective baud length is maybe 1 microsecond or 0.5 microsecond or 0.5 microsecond, so that my range resolution is much higher when compared to this size. And coming to the TR module, so once the exciter is generating the low power RF signals, once it reaching the antenna field, the required peak power, like 1 megawatt of peak power or such type of things has to be generated in the atmosphere. So here in each TR module, we are generating 1 kilowatt of peak power by using solid state devices. These MRF 157 devices are used here. So it will be generating obviously 1 kilowatt peak power, and your ST radar Kolkata is having 2 kilowatt TR module is being used in the same configuration. And basically the TR module has one transmit block, which is generating this 1 kilowatt or 2 kilowatt powers using 3 different stages: pre-driver amplifier, driver amplifier, and power amplifier. In that way it is generating and it is giving to the antenna. And the receive path, as I told in the earlier slides, low noise amplification has to be done. So that low noise amplification is done in the receive path by using LNS here. And the phase shifter, whatever till now we have seen, the phase shifter has to be, progressive phase shift has to be given for different antennas. That phase shift, once it is calculated, given to this phase shifter network, and each TR model, once that phase shift information is given, the switches have been activated here, and the required phase information will be provided here. And there will be TSG card, that is timing and signal generation card, FPGA card will be there to communicate with the radar controller to say that I am alive, or I am giving this much of peak power, or my phase information is this much. To communicate that, there is a TSG card here. And these transmitters, you can see, surprisingly they are kept in outdoor itself. And for this one, the lot of heat is generated, that will be through passive cooling. But if when you compare to this ST radar, there is having hut. There will be some 2 ACs are there here. Through the ACs, the TR modules are getting cooled. So the 2 different type of technologies are there, how to handle this type of peak powers. And these are the different waveforms that you can see here. Once it is given the frequency time domain, you will be looking the signals like this. When you go to the frequency domain, the sync function FFT of this one, if you do this, looks like this. And the bandwidth of the transmitter is almost like 11 megahertz in TX field. And in the receive path, it is around 10 megahertz bandwidth is there. And this is a phase shifter, how we are controlling with different phase bits have been systematically shown here. And this TR model is having sensitivity almost like minus 110 dBm of the signal it is sensitive, and almost up to plus 10 dBm signal it can take it. And the band limiting of application and the required boosting of the signals to the ADC level has been done in multi-analog receiver. Here we are having 18 channel receiver we are having. Each channel is having 65 dB gain and a beamwidth of, bandwidth of 2 MHz or 4 MHz based on your range, your baud length. If I am using a 1 microsecond baud length, I will be going for a 2 MHz bandwidth I will be using. If I am going for a 0.5 microsecond or so, I will be using 4 MHz bandwidth. And finally, this is the digital receiver where till now we got only RF. Once this RF signal has to be converted into the digital domain by using ADCs, the analog to digital conversion has to be done. Here 80 MHz clock is given to this one, ADC. So samples are, we are getting at 80 MSPS, and then digital down conversion. So previously, what used to happen is, once a radar is transmitted with a carrier of 53 MHz, they may be bringing down to 5 MHz or so. So then IF signal we are calling. So we will be bringing it down to the IF region. Then finally we will be used to process. But the technology now offers high-speed ADCs, and almost like currently we are having up to, with the RF SoC, RF system on chip technology, almost like up to 4 gigahertz. Sampling speeds also we are having ADCs, and we can process also, but for the time, for our radar we are having 80 MSPS ADC we are having. Then digital conversion, that means your carrier is totally removed. Only I want only Doppler information, which may be hardly maybe not more than 10 Hz, or sometimes it will be 1 Hz or 2 Hz, it will be usually that. So that information I will be getting through direct digital conversion I will be doing. Then further, coherent integration or any other signal processing steps I want to implement, I will be implementing in the FPGA available in the digital receiver. So this is the sensitivity of the digital receiver. Almost this has dynamic range of 80 dB, almost from minus 75 dBm to plus 10 dBm it has the capability to receive the signals. And this is the radar controller I told, this is the brain of the radar system. This controls all the people. All the subsystems and all the experimental sheet parameters will be configured from here and will be controlling given to the TR model located in the field through Ethernet communication. And also I want to know that 1,000 numbers are there, whether they are participating in the experiment or they may be gone bad. So that information we can get back from this radar controller, and further we can go for maintenance if something is found faulty. These are the different timing signals that is generated by the radar controller for the synchronous operation of the radar. And most likely this techniques, and what technique I have to use for different science applications are shown here. One is the DBS technique, where usually 5 beams, usually 3 beams are sufficient, but 5 beams are used here for getting the zonal velocity and meridional velocity. Here, suppose if I am keeping a east beam and a west beam, by using, if you are resolving the vectors here, by using these two things, maybe like when you are tilting the beam with an angle of theta, so the east beam can be resolved like u sin theta and w cos theta, where u is the horizontal component and w is the vertical component. When you are tilting the beam, we are having both vertical component is there as well as horizontal component is there. So if I can remove the vertical component here, I can get back the horizontal wind velocities I can get by using east and west. Similarly, if I am positioning the beams in north-south directions, I can get meridional velocity of v, from which we can get u and v, zonal velocity and meridional velocity. Usually typical power spectra of east beam, west beam, zenith beam, north beam and south beam looks like this. You can see the range of the spectra almost from 1.5 kilometers to 22-23 kilometers. You can see the Doppler usually in the order of 2 to 3 hertz only. This is what very much important for any VHF radar or wind profiler system. Here we are having a lot of clutters will be there. Extracting 1 Hz or 2 Hz from 53 MHz or 200 MHz, very, very tough. They are having nearby, suppose we are having some hills are there, or a system is locally generating some 53 MHz signal or carrier signal. That has to be removed sufficiently from this range of spectra. The clutter removal, lot of clutter removal techniques are there, but it is different from system to system. If I am designing one clutter technique for one radar system is not sufficient, based on the nature of the, let us say, one best example I will give you here, 1 minute I will take. Nainital system, which is totally surrounded by totally hills. There was having lot of clutter, clutter nothing but the signals are, instead of giving this Doppler, totally they are considered at 0. That means non-moving targets. They are getting that type of problem. Finally, they traced that a clutter fence, when you are using properly to minimize this clutters, then the problem has been solved. Similarly, here also you have used some clutter fence. This is called a clutter fence. It has been implemented in Kolkata University also. And also software wise, you have different clutter removal techniques we are having. So that will be effectively, once you are using only, you will be getting, you can find the proper peak, and will be, you can derive the zonal and meridional velocities. And since we are having advantage of this active phase radar system is fully azimuthal beam steering we can have. Apart from not only putting the beam in particular directions, we can steer the beam in different azimuthal directions. We can have at a different elevation angles. Once you are going for this type of configuration, you can study the anisotropy and much more other information you can get from the atmosphere things you can study. And in the afternoon sessions, Anand sir will be taking off this space data receiver techniques, and some techniques sir will be dealing with that. And here, so basically, this will be used for the vertical beam will be pointed, and if you are three different, multiple receivers will be can use it for extracting the same wind information at very high temporal resolution of almost like 10 seconds or so, we can get back this information. And also the advantage of this phase steering is, if you want to steer the beam, point the beam simultaneously in different directions also, we can put it, and we can derive the winds at much higher temporal resolution, much lesser temporal resolution when compared to the normal things. And also this is one of the applications where you want to have the angle of arrival for interferometer techniques. We can use different type of you can select different receivers, and also if you are pointing the beam towards ionosphere or something, we can from the phase coherence and the phase functions, we can get back the angle of arrivals and further information we can get. So these are the glimpse I want to give that radar is a powerful tool which is having not only complex electronics, but it is giving more utilities for user scientists for different applications. Right from the troposphere, you have stratosphere, some of the lower stratosphere you can study, and you can study your mesosphere echoes, you can study, ionosphere you can study, and the morning as is shown, if you want to go for imaging type of thing for a moon or something far distant object, we can study for that. And when you get a weak echo from the atmosphere, which is in the order of minus 160 or so dBm, if you have a hard target in the space, like a space debris, so those information will be much easier to get from this type of radars. So the applications are versatile. So if you are using the radar in a proper way, if you are designing the proper radar in a proper way for your scientific requirements, we can use for many applications. So thank you very much.